All right, today we are jumping straight into the world of chemical kinetics to solve a little puzzle. And believe it or not, our whole investigation is going to start with just one kind of confusing sentence. But inside that sentence is the key to unlocking a really big idea, the first-order rate constant.
So here it is. This is our source material. And yeah, at first glance, it just looks like a total jumble of scientific terms, right? It's a bit of a mess, but buried in there is actually everything we need to understand how chemists figure out the speed of reactions. Our job today? To translate this thing.
Which brings us to the big question. What is this quote actually trying to tell us? And more importantly, how can we use its own logic to figure out the units for something called a first-order rate constant? So let's break it down, piece by piece, and we're going to start with the absolute basics.
First up, we've got to get a handle on what the source means by speed or velocity. In the world of chemistry, we just call this the reaction rate. And this is the starting point for everything else.
Put simply, the reaction rate is exactly that. It's a measurement of speed. It tells us how fast the ingredients we start with, the reactants, are getting used up, or how fast the stuff we end up with, the products, is showing up. It's pretty much the heartbeat of a chemical reaction.
Now here's what's so cool about our original quote. It actually gives us the formula right there in the text. It says concentration per time. And that perfectly lays out the two things you need to measure a rate. How much stuff you have, that's concentration, and how long it takes for that amount to change, that's time.
So if we put those two ideas into the standard scientific units, we get the first piece of our puzzle. We measure concentration in moles per liter, and we measure time in seconds. So the unit for reaction rate becomes moles per liter per second. A key insight pulled directly from that messy source material.
Okay, so we've got the rate? Check. Now let's get to the next piece of this puzzle and see how it all builds up. What in the world makes a reaction first order?
This right here, this is the key equation. It's called the first-order rate law. And all it's saying is that the rate of the reaction is equal to some constant, we call it K, multiplied by the concentration of one of the reactants. It's a really nice, simple relationship.
So what does that actually look like? Well, in a first-order reaction, if you double the concentration of that one special reactant, you double the reaction speed. It's that simple. And that little K there, that's the rate constant. Think of it like a unique fingerprint for every reaction at a certain temperature. And finding the units for that K, that's our whole goal here.
All right, we have all the clues we need, we know the units for rate, and we have the equation that ties everything together. So now, finally, we can solve for the units of our rate constant, K.
And all it takes is a tiny bit of algebra, If rate equals K times concentration, then K has to equal rate divided by concentration. We've just isolated K on one side, which sets us up perfectly to find its units.
Now for the fun part. We just plug in the units that we already figured out earlier. So for rate, we pop in moles per liter per second. And for concentration, we use moles per liter.
And here is where the magic happens. See that? We have moles per liter on the top of the fraction, and we have moles per liter on the bottom. And just like in basic math, when you have the same thing on the top and the bottom, they just cancel each other out. Poof!
So what are we left with? Just seconds inverse, or s to the negative 1, which is just another way of saying per second. And there you have it. We actually did it. We used that super confusing quote to find the units for our first-order rate constant.
Okay, so we found our answer, S inverse, but who cares? Why does that even matter? What does per second actually tell a chemist? Well, this is where it gets really, really powerful.
Here's the most important takeaway. That unit, S inverse, or per second, it acts like a unique fingerprint. If you are ever looking at a rate constant and you see those units, you know instantly that you're dealing with a first-order reaction. It's a dead giveaway.
And this is just incredibly useful. You don't even need to see the chemical equation. You don't need to know which reactants are involved. The units of K all by themselves tell you the reaction's order, which is just how its speed depends on concentration. It's this amazing shortcut that lets chemists immediately understand the basic behavior of a chemical process.
And that kind of leaves us with one last thought to chew on. We've figured out the signature for a first-order reaction, but what about all the other reactions? If a rate constant has totally different, maybe more complicated units, what could that be telling us about the intricate dance that its molecules are doing? Something to think about. Thanks for tuning into this breakdown.